You need solutions for your most complex challenges, comprehensive results that help communities, economies, and natural places thrive. We're the team whose engineering and environmental expertise delivers these outcomes. Around the globe, our engineers, scientists, and technical specialists focus on solving our clients' problems as if they were our own. With BAR's resourcefulness and dedication, you'll find solutions in engineering and design, environmental investigation and remediation, permitting and compliance, sustainability and resiliency, and water management. All our work begins with listening, because your problem deserves a tailored solution from consultants who share your passion and integrity. Because your evolving needs require an agile partner who can dive in and assist at any point along the way. We're here at every step to deliver an exceptional experience, sustainable solutions, peace of mind. Together with BAR, you'll find the best answers to your biggest challenges. At BAR, we're here to help you with your mining project from concept to closure. If you can mine it, smelt it, move it, or store it, we'll be there. If you can design it, build it, power it, or repurpose it, we'll be there. We help with environmental services, mine geology, mineral processing, material handling, facility and site design, plus tailings management. We'll be there for water resources management, field performance monitoring, mine closure, remediation, reclamation, and more. We'll meet you at any step of the way. We're an employee-owned company with world-class expertise and a nimble, flexible approach that puts you first. Our commodities experience extends from nonmetals and industrial minerals such as potash, coal, and sands, to metals such as iron ore and copper. From precious metals such as gold and silver to rare earths. You need consultants you can count on. If you can dig it, process it, or store it, BAR can accomplish it.
Welcome to our structural, mechanical, and electrical focused webinar titled Modern Engineering Design Technologies and Practices for Plant Retrofit Projects. I'm Brad Dunn. I'm a senior mining geologist at BAR, and I'll be your host for today's webinar. Thanks very much for joining us. Today's webinar will provide valuable insights to help you make decisions when you're looking for engineering services and to add value to your projects. So BAR Engineering has assisted national and international mining and minerals processing clients with complex, large-scale projects for more than 60 years. We offer assistance with everything along the mining development lifecycle, and by integrating our engineering and environmental expertise, we can provide a streamlined approach to your project, one that improves efficiency, communication, and understanding of both the small details and the big picture. So today we're going to be hearing from Jesse Altman. He's a senior mechanical engineer. Jesse has 13 years of engineering, design, and project management experience. He's worked through all phases of projects, including concept development and trade-off studies, pre-feasibility studies, feasibility studies, detailed engineering design and analysis, modeling and drafting, construction coordination and management, owner representation, and commissioning. Currently, Jesse works primarily on multidiscipline engineering projects in the mining and mineral processing industry in the Midwest and Intermountain West. We'd like to, before we get into the details of the presentation, we'd like to start with a safety share. And this is a personal story for me. In March 2020 in the Salt Lake City Valley, we experienced a significant 5.7 magnitude earthquake. I was at home awaiting a solar panel installation on the roof of my house. So right after the main shake happened, the installation crew showed up on my doorstep. And I'm a geologist, so immediately I started thinking about the safety ramifications of people being on my roof. I explained to them that I wasn't comfortable with them being on my steeply pitched roof because of the expected aftershocks. And we did end up experiencing hundreds of aftershocks for this particular earthquake. So the installation crew wouldn't leave, and they were quite adamant that their manager, their boss, had told them to do the installation. And I pressed and really reiterated that I didn't want anyone on the roof of my house. So I had to call their manager and explain that the safety risk was too great to have them up there on my roof. And sure enough, about an hour after that main shake, there was a significant aftershock that was almost as strong as the main earthquake. Eventually, when the installation crew did turn up back at our house a few weeks later, they were very appreciative. They were my best mates that I'd made that call on safety, and they weren't on the roof when the aftershock happened. They reached their workshop, and that's when the aftershock happened, and they were quite taken back at the strength of it. It's a nice ending to the story. The installation was safely completed a few weeks later when the aftershocks had significantly died down. So the moral of the story of this safety share is it's important to always put safety first, even when that means having difficult conversations. So that's the safety share, and I will just repeat that in our final segment. I'll return to moderate the responses to your questions and share through that Q&A function that I described. With that, I will hand it over to my colleague, Jesse. Thank you.
Thank you, Brad. Thank you, everyone, for joining us today. I'm happy and honored to be doing this for BAR, and I'm excited about this because this is my career, this is my engineering life, and prior to coming to BAR, and I've been with BAR for 3 years now, but prior to this, I worked for a mining company where I managed engineering and construction projects, and found that engineering budgets and schedules usually went over when we, as the owners, changed some of the process design criteria or preferences along the way. Then it took the engineering companies a lot of time to reproduce calculations, design specifications, and drawings. And then when it came to construction, typically our change orders resulted from interferences found in the field during construction. And now coming to BAR, I'm seeing the design tools and the engineering tools we're using that are streamlining our design approach and eliminating these interferences that are realized in construction, costing the owners extra money. So I'm not necessarily going to be presenting newest cutting edge technologies, but rather the well-established industry tools that we use now to improve project designs and reduce construction costs. I'm going to highlight some of the technologies and practices that we use by walking through a case study project. So full disclosure, this case study project is mainly one actual project recently completed for a heavy industrial facility retrofit. However, I'm borrowing little snippets from other projects and then intentionally kind of changing details of the case study project to protect confidentiality. So this project was a retrofit to a mineral processing facility that mainly took place in the concentrator. There were millions of dollars of new process equipment that had to be tied in to the existing concentrating process, as well as all the mechanical interconnections such as chute work, piping, duct work, gravity flow launders, etc. The structural scope included remodel to the existing facility, as well as an all-new building built adjacent to the existing facility. And the electrical scope also included remodel and new infrastructure. So it's kind of the quintessential retrofit project, relatively large scale, you know, tens of millions of dollars estimated in construction. And well, I guess that's about it for the project for now. So for the sake of organizing this presentation, I'm going to walk through kind of linearly the design process for these retrofit projects. In reality, these things take place with all engineering disciplines coordinating the whole time. But again, for the sake of organization, I'm going to start with the step of capturing existing conditions. So in this step, traditionally, these projects begin with receiving from owners and reviewing many dozens or maybe hundreds of reference files. Those are mainly original plant construction drawings, which are these days generally 30 to 50 or 70 years old. They're very outdated. A lot of remodels that take place over time aren't necessarily documented. Then we also review design deliverables from remodel projects that were executed over time. And then there's an extensive amount of field work to walk down existing systems, take photos, take measurements, and then try to build an accurate picture of the existing condition of the facility. So this process is really time consuming and expensive, both on the engineering end and for the owner. And then it usually results in incomplete and inaccurate picture of the existing condition of the facility. So the biggest time saver that I'm enjoying now and that we use is 3D laser scanning to capture the physical state of the existing facility. So 3D laser scanning is a survey method that captures a point cloud of XYZ data points, millions of them, inside and outside of existing facilities. It's so resolute and refined that you can see small piping, wires, boxes, bolts, equipment, all the mechanical interconnecting materials, the structural and architectural features, everything. So on this next slide, we see an example of viewing the 3D scan after it's done from the main 3D scan view software. Each one of these little pyramids here represents a scanner setup point. So this is a physical device that's very easily managed by one person, where you walk around, set up the device, and anywhere between 1 and 2.5 minutes, you take a 360-degree scan of the facility from that point. Then you walk around and repeat the scan process in multiple different locations to get every angle covered that you're going to need for design. So as I said, it's maybe a minute to 2.5 minutes per scan. That depends on the level of resolution that you determine you need to capture, and then also whether you have photorealistic imagery. And here I want to show, using CAD software after the scan has been post-processed, how you can move around within the scan. I'm going to pause at a few points here, but as you can see, this is inside of an existing facility. It's as if you're walking around the facility. We have photorealistic coloring on. This was actually a low resolution scan, so there's not nearly as many data points as there could be if you needed to pick up 1/4 inch reagent piping, for example. Using the CAD software of the 3D scan, you can click from point to point in the scan data and measure between, for example, this foundation here and this foundation over here. You could measure beam web thicknesses. You can measure diameters of pipe, distance between pipes, locate actual equipment, installation bolts, and everything like that. The scan that we're looking at right now, my colleague and I completed on New Year's Eve day. This was all we had to do to capture all the physical reality of this facility. We drove down morning of, a few hours away from the office, I'll say, and then completed a scan of roughly 60 setups. So 60 scan setups, and then got some more field information, met with the client, and then we were home by New Year's Eve dinner to have dinner with our families. So compare that to multiple days of poring over reference files, usually multiple site walks for each discipline. You may have mechanical engineers and designers that have to walk down the mechanical systems. Same story for structural and electrical. And then you are generally still left with an incomplete or inaccurate picture of the facility. The case study project was about 1.5 days of scanning and post-processing, and there we had a real picture of the facility in its current state. And then another huge benefit of that is we're able to deliver that 3D scan model, the point cloud, to the owner, so they have a record set of the facility in a 3D format. So we don't use 3D scanning on its own. We oftentimes accompany that with photos and measurements from the field. And then another useful tool for 3D scanning is structural assessments. And I wanted to share this example here, where this is a conveyor structure for a loadout of a mining facility, where they were experiencing, they believed, some shifting of the structure over time. We were able to set up the 3D scanner and produce this 3D model of the existing structure, and then compare that to the design files for that loadout structure and pinpoint where the deflection was occurring, and then actually find where the failures had occurred in this structure. So I wanted to point out another side benefit to 3D laser scanning, and this particular project is going to come up again a little later. So now I want to talk about process and mechanical engineering and design. 3D scanning is what we use to capture the physical state of the facility, but there's a lot of process information that's not picked up in the physical world. So the way we gather that information is usually process flow diagrams, sometimes piping and instrumentation diagrams received from the owner. We go through historical process data generated in PyHistorian or other softwares like that. And then we collect and use process equipment information by gathering nameplate information, cut sheets, O&M manuals for the existing process equipment. All of that is used to then develop a process model using process modeling software such as METSIM, ChemCAD, Bruno, Aspen, HSC Chem, EggFlow, and JK-SimMet, to name a few. For the mineral processing projects we undertake, if they involve slurries or solids and particle size separation, magnetic separation, those types of, and comminution, METSIM is our go-to. So this image we see here is a screenshot from a METSIM model. So after we've built a model of the existing facility, we're then able to add the new process equipment and process streams based on vendor test data, third-party lab data, and major equipment performance specifications. So setting up the model is faster than developing a flow sheet by hand and then accompanying that with hand calculations for mass balance or other chemical processes. But where it really benefits us is when the design or the process design changes in the future. You're able to quickly update the model that's constructed in the software and then reproduce all your outputs, such as a mass balance table, in just a few clicks of a button and in minutes instead of hours of reproducing all the hand calculations to produce the same outputs. So when the process model is developed and refined, we're able to identify all the stream flows from equipment to equipment and the process performance criteria of the equipment itself, and then move into the mechanical engineering scope, equipment specifications and design. One of the analytical softwares I want to bring up for mechanical engineering is AFT Fathom and AFT Aero. In the case study project, which was mostly a wet processing project, mostly slurries and liquids, we used AFT Fathom, extensively. This software coordinated with the 3D design of the mechanical systems. So the systems only had to be designed or drawn up once, and then the design file was able to be imported to the analytical model to produce the engineering analytical results. A huge benefit of this software is that it's cataloged with piping materials, all the sizes that you would use, materials that flow through the pipes. There's catalogs for those. You're able to set up the slurry parameters for each different part of the process, and then all the piping appurtenances such as valves, tees, elbows, reducers, etc. You don't have to look up individual friction factors or other criteria for the parts of the hydraulic model. Instead, you select them from catalogs, and you're able to build an accurate hydraulic model of the facility very quickly. And then you experience further benefits when the design changes periodically. For example, if the number of pieces of a certain type of equipment changes, and then you have now more pipes and different sizes, The model is updated in just one software, namely the 3D piping design, and then that can be re-imported to the analytical software. Again, a few clicks of a button and you have your new analytical results to complete your designs. Then with the 3D design development of piping, for example, we're able to output the two-dimensional drawing views and isometric views very quickly from the 3D design, as well as produce the bill of materials. And this is just looking at one sheet from the case study project. When the piping is designed, we select materials from the catalogs within the 3D design software, and then bills of materials are generated automatically rather than going through design drawings by hand, quantifying couplings and elbows and pipe lengths, etc. We've also used fluids analysis software for gas flow and heat transfer calculations and design. I mentioned AFT Fathom for liquids and slurries. AFT Aero is another software that's extremely helpful on more gas flow or compressible flow systems and for heat transfer. So on this project, we had to redesign the exhaust ductwork for some existing kettles, I'll say, and the exhaust gases were very hot and causing extreme heat and deflection issues in the existing ductwork, and all of it was basically failing and needed to be redesigned. So we're able to do 3D design of the new ductwork and then import the geometric design into the analytical model to determine things such as correct ductwork materials and thicknesses, insulation specifications and thicknesses, to optimize the new ductwork design to achieve the heat and friction goals of the new design system. So it made for really efficient reiterations of the design to optimize the mechanical criteria. So for projects that include bulk material handling, I've been talking about just wet systems so far, the main two tools that benefit us greatly are conveyor analytics and bulk flow discrete element method simulations. So this is looking back to that loadout conveyor system where we used 3D scanning to determine where the structural deflections and failures had occurred. Because of those structural issues, the conveyor inside this loadout gallery was no longer usable. So as you may recognize, a loadout infrastructure is basically lifeline for a company to sell its product and make money. We needed to minimize the amount of downtime and get a loadout system working again. Using the conveyor design tools that we use, the softwares for component selection, load criteria, belt tensions, and power, we were able to inventory the equipment that they had on hand as critical spares for that loadout system because it's such a critical system, and put together a design using components that they already had on hand for a new temporary loadout facility to be used while they were making the repairs on the mainstay loadout facility. So we were able to complete this design way quicker than would have been done using hand calculations and two-dimensional design, analyzing, reverse engineering and analyzing the parts that they had on hand. This conveyor design software had all of those parts and components in the catalogs, all the load criteria, etc. So we produced a design quickly and got them back running on their loadout system while the incumbent loadout system was undergoing the structural repairs. Then beyond conveyors on your transfer points, we use bulk flow simulation softwares to give a better idea of how the actual particle sizes, bulk densities, and other factors of the bulk materials are gonna flow through the chute designs. On this project, we were replacing some existing screening equipment with new screening equipment whose geometry was quite different from the existing equipment. So the chute work design had to change. This was an existing plant with a lot of equipment and piping in the area. And so the piping, large process piping, constrained the design of a transfer chute between the screen and a takeaway conveyor. So this image, this animation upper left here I'm going to play now, shows how the material was simulated to flow through a chute design that would not require any relocation of existing facilities. I'm going to play it again and pause it here. You can see that the chute was prone to building up material and eventually plugging right here. So the client, of course, wanted to avoid having to reconstruct any of the other existing facilities. But using this bulk flow simulation, we were able to get a good idea for how a smaller geometry chute would perform compared to an ideally designed chute with just basically a deeper cross section and a steeper slope. So this simulation effort was done within a day. We were able to very quickly justify the cost of rerouting some of the existing process piping to move out of the way to make room for an adequately designed chute. On the other hand, we could have avoided that redesign cost or reconstruction cost of the interfering process piping, but they would have then experienced hours and hours of downtime in the future due to chute plugs, and that would turn out to be a lot more expensive than the initial cost of process piping reroute. So that's one of the benefits of the simulation of the bulk flows. Compared to that, it's basically engineering judgment on how these transfer points are gonna, I don't want to short sell it. There are calculations and everything, but the simulation is proving to be much more effective, accurate, and time saving. So when we use the 3D design tools, we design the new systems on top of the point cloud that was generated in the 3D scanning phase. This allows us to design around the structures, equipment, and mechanical and electrical systems that have to remain in place, and then produce designs that don't result in interferences. This is from the case study project. You see the gray dots that are representative of 3D scan point cloud data. So here we're inside the expansion part of the process, outside of the existing facilities. A little further on here, you'll see where we flow through an existing wall and inside of the existing building. So here we can see existing columns that we're going to tie into. We see existing equipment over here that we're adding on to. And then you can see some interferences occurring up here. This was so useful in developing the demolition views for existing structures, piping, etc., that is not needed in the process going forward. So this is what the actual 3D facility design looks like on top of the existing facility. To give a sense of the time savings on this particular project, we've come up with an estimate for doing conventional 2D design of new facilities, not doing 3D scanning, and then not using some of our latest analytical tools. And we had estimated about 1,400 hours for just the mechanical engineering and design scope. In reality, we did 3D laser scanning, 3D design of all of the project discipline work, and ended up spending about 800 hours on the mechanical scope of work. Another thing I want to qualify is that 1,400 hour estimate was done at a point in time when the process flow sheets would have been finished or frozen. And in reality, this 800 hours included a couple different iterations of process design changes. So the mechanical equipment layout and interconnecting systems designs feed right into the structural and electrical. And again, we're coordinating along the way, but for the sake of presentation flow, I'm going to now move into the structural scope. The main structural engineering and design approach we take includes, again, 3D design of all the structures, and then using structural analytical models. We gain the most from these tools on large, complex projects where simple beams or small platforms don't necessarily require these tactics. On the case study project, we were able to produce a structural model of the existing facility from the 3D scan. So the 3D scan picks up on column depths, beam sizes, connection types, etc., where we're able to quickly reverse engineer it and build a model of the existing structure to be used in analysis. We're able to model foundations with their real geometry, columns, beams, and then apply existing equipment, live, dead, and environmental loads to the model to get an accurate record of its structural capabilities in its current state. We then integrated the 3D layout design of new equipment and mechanical systems onto the structural model, and then added structural loads, and then designed new structures such as equipment supports and catwalks, and applied them to the modeled existing structure. This allowed us to efficiently identify reinforcement needs, improve the load flows, optimize the new structures that we were adding, and then do all the stress and strain analysis and service criteria such as vibrations, deflections, dynamic loads. This was the best way to produce a safe and efficient structural design, and to do so using less engineering time. And what I mean by an efficient structural design is you can shorten your hand analysis by over designing, and using these models, we're able to use the right capacity of structures to make for a more efficient or less costly structural design. Then, like the mechanical systems, the structural design can change over time. If the process flow changes, then the amount or sizing of equipment changes. Downstream from that, piping, launders, chutes, all of that changes. You end up with new loads occurring at new locations. Well, once a 3D model has already been built and a 3D analytical model is built, you can quickly move your beams, move your connections to accommodate the new load points, and then very quickly resize any members where required, add reinforcements, etc. This is also very helpful in cross-discipline coordination to have the 3D design set up. These 3D designs between the different disciplines coordinate with each other, and then the 3D model of the structures is also useful in preparing the drawings. Just wanted to name a couple of the 3D softwares we use, analytical and design. Mainly analytical would be STAAD and RISA 3D. So we can also deliver that structural model to the facility owner for your future reference or for future modifications. Now I want to move to electrical engineering and design. So we discussed how we capture the existing conditions early on, but again, mostly in the physical world. So for electrical systems, to be safe, reliable, and code compliant, there has to be careful, thorough engineering and analysis, followed by clear and comprehensive documentation. We found that the best way to do that is by developing power system models using softwares such as SKM and ETAP. In the case study, we were actually given a power model of the existing facilities. However, normally we start out with a hand sketch, such as what you see on the screen here, and then gathering information in the field. So when we gather information, we start at the main substation, walk down through smaller substations, through the switchgear, MCCs, follow busing and wiring, and finally down to the equipments and the other loads such as lighting. Gathering this information in the field, then we produce an electrical power model using the power softwares I mentioned earlier. The model is useful for coordinating of the power system, specifically with new infrastructure going in. It's used for producing the short circuit calculations, load flow analysis, and then completing arc flash studies. So speaking of coordination, if coordination isn't done properly, trips can occur at the wrong level. So one of our clients' underground facilities experienced such a thing on a system that was not modeled up. They had a single line diagram for the facility, but no power model. So this is a mock-up, not the same single line, but just for the sake of talking through this, this is the level where a trip occurred on a small transformer tail end of the power system. If it had been coordinated properly, then a breaker at this 120 or 208 volt panel would have tripped, and just this circuit would have gone without power. Wrong settings in that breaker could have tripped the main breaker on this panel, and all of this would have been without power. Moving further upstream, if this panel didn't trip, you could trip a breaker here at the 48 volt or 480 volt MCC, and this whole leg goes without power. I'm sure you know where this is going. The system was not coordinated properly, and the trip actually occurred all the way up here at the main substation, and the entire underground facility was without power. This was 25% of the site, and it resulted in miners being temporarily stranded underground and stuck in the shafts. So the power model is used for coordinating the power system so the trips occur at the proper level. The power model produces time current curves such as you see here. And then it's also used in developing single line diagrams. The model can actually output a start of your single line diagrams. There's an example of one seen there. The power model also will give you bills of materials, cable schedule, panel schedules, all the design deliverables that are used for procurement and construction. Then lastly, the power system model is used for arc flash analysis. So arc flash analyses are required by NFPA 70E. And the model will give you the correct arc flash boundaries for the equipment, the hazard levels of different equipment, and then BAR is able to, using that information, develop information for the arc flash labeling, and then we actually produce those labels and can install them in the field. So building the power system model makes the iterative process much more efficient, just like as discussed in mechanical, structural, and process. So if the electrical design is halfway done and then the process design changes, the model's already been built, new loads are added, the calculations are reproduced in minutes, and the design can be adjusted as necessary for a safe and reliable electrical design. Again, producing new iterations in minutes to hours instead of days to weeks. So in addition to the other deliverables discussed, such as single line diagrams and cable schedules, we will deliver the power model itself so the owner can continue to use it in the future, just refer to it in the future, or provide it to its other engineering consultants for updates on future retrofit projects. So that was all power modeling, or sorry, the engineering analysis side. As far as design deliverables, we are also doing electrical routing and lighting using softwares that model up lighting, for example, and then 3D design of electrical raceways. So by designing cable tray and conduit, box locations, etc., in 3D design packages, we're able to coordinate that with the structural and the mechanical designs so that there are no interferences in the field when it comes to construction. I can recall many times where electrical construction contractor moves into a project kind of last, and everything is drawn up where the cable trays should be routed. Turns out there's a piping bank there or a column, and everything has to be rerouted, and it costs you $30,000 every time. So in the case study project, we developed each discipline's design models using just a couple different softwares. We use many different softwares, and on some projects we end up using several. And in those cases, there are intermediary softwares that can take the design outputs from all the other 3D design softwares, integrate them into one. So what we normally do then is integrate the 3D designs about once a week to check for interferences and coordinate as a team. Give you an example of one of those softwares. It's an Autodesk product called Navisworks. Navisworks Freedom is a specific product that you can download for free online and use. And then there are higher levels of utility for Navisworks that we use as well. So on the case study project, for design reviews with the client, rather than producing drawings at a 30%, 60%, 90% completion level and sharing dozens or hundreds of drawings for them to review and provide comment on, we just did design reviews using the 3D modeling as we were developing it and didn't spend time on generating drawing views until the design was complete and accepted. And then we were able to produce the drawings all in one shot. By keeping a combined 3D model, we're able to develop those conventional drawings from the combined model just by turning certain layers on and off and then selecting the plan, elevation, or section views, defining up those the way you want them, and then producing them in two-dimensional space like you see on the screen here. And then if something changes in the design file after the drawings are made, you don't have to redraw every line in two-dimensional like it is required in 2D design practices. The model is updated, the viewports are updated, the dimensions move automatically, and there's just a few cleanup steps and the drawings are ready to go once again. So my goal today was to demonstrate how the 3D design approach was more efficient for our recent retrofit projects. We're well past the learning curve of initial 3D design softwares, both for the software developers and then their early adapters. It's now much more efficient than a conventional 2D design and drafting approach. Streamlining the coordination between the disciplines reduces our engineering costs and therefore the owner costs. An example of that is our time per design deliverable is going down consistently as we're getting better and better at the 3D scanning and 3D design method. So our design time goes down, project costs are not going up as time is going on here. So another goal was to demonstrate how 3D scanning and 3D design combined produces more accurate design outputs. So that avoids interferences and then reduces the construction costs. It also provides a more accurate documentation for your facilities as record sets for you for reference in the future and for future projects. So we've also found that the analytical softwares we've discussed is much more efficient and accurate when designing these large complex systems. The analytical tools perform the calculations very fast. They provide catalogs of factors, material databases, etc. to be used in the analysis. And then as projects evolve, new iterations take minutes to produce instead of hours to days for computations and new outputs. And then for your benefit, finally, those analytical models we can deliver for your future use. So this presentation just showed a portion of the services and capabilities that BAR provides for our clients. Because we're all about client service, our disciplines coordinate with each other. We work together throughout the entire project to give you a comprehensive look at your project. But if all you need sometimes is one discipline, just one structural analysis, or electrical power model, we're not going to push all disciplines on you. We'll provide just the scope that you're looking for and tailor it to suit your needs exactly. And if you want to talk more about our services and capabilities in general or anything specific in this presentation, you can contact me or Brad Dunn. The emails are going to be displayed at the end of this presentation. Thank you all again very much for your time and looking forward to your questions. Back to you, Brad.
Thank you very much, Jesse. So we do have some questions that have rolled in during the presentation. So I'll read them to Jesse now, and we'll talk through that. So the first one we have is a facility scan best done when they are on shutdown?
I'd say the short answer is no. We normally do the 3D laser scanning while a facility is still running. The caveat is safe access. So if you need to get views at rotating elements and there's guards because personnel cannot be inside, you'd have to shut down that piece of equipment to remove guards and get closer to the piece of equipment. But like I said, shortly given, if you can walk around the facility with it running, then we can do our 3D scanning with the facility running.
Right. Next question, what software do you recommend using, and why don't you use one software for everything?
Well, second part first, just like tools in construction or maintenance, there's no one tool that accomplishes everything. So we do try to streamline by minimizing the amount of different software packages we use on a project. However, There isn't one software that does both structural analysis on structures and the fluid flow analysis for piping, for example. So to give you a few recommendations, softwares that we use most commonly, I would say in 3D design, we're using Autodesk, CADWorks, and then SolidWorks in the mechanical world. Also Revit, and then Revit is also used largely in structural as well as RISA 3D. Electrical 3D design, we can use the same CADWorks. CADWorks has catalogs of cable tray even for generating bills of materials for raceway runs, and SolidWorks on electrical 3D design. Then on the analytics, we use, I'm going to blank on the bulk flow modeling name now. For wet systems, or I should say fluid systems, AFT, Fathom, and Aero. Excuse me. We also use ANSYS CFX for finite element analysis. We can do stress and strain analysis using SolidWorks on smaller objects. We do main structural analysis using RISA 3D and STAAD, S-T-A-A-D. And then for electrical power models, I'm most familiar with SKM and ETAP. And then I mentioned, and I really like this one. This was a game changer for me coming to BAR. Navisworks software, free download of Navisworks Freedom to look at 3D design files. Our clients love it. They're able to accomplish, days of drawing reviews in minutes or an hour of reviewing a 3D model. You spin it around, you move yourself through the nooks and crannies. It's like you're walking through a mock-up of the plant.
Great answer. Got another one here, and it's somewhat related to that line of thought. Can the wet or dry bulk handling software be used to optimize systems for wear or plan for maintenance? For example, chutes for conveyors or elbows and slurry pipes, that sort of thing.
Sure. I don't have a ton of experience with the bulk material handling simulation, but I do know we've used it to force dead beds, for example, in a chute. So when you have change of direction of falling rocks, if you create a dead bed on purpose but not constrain it such that it chokes and plugs, you save on wear life. And then we also get the impacts and the velocities of the bulk materials as they flow through chutes. So you can optimize that design to get the material moving the right velocity and impacting in a way that doesn't accelerate wear on the surfaces. Then on conveyors, for example, the conveyor design tools we use give us the loads on all the components. So idlers, pulleys, bend pulleys, and all of that. We get the loads on those components so you can select the correct bearings, shafts, etc. for the desired design life. I hope that answers the question.
Great. So that is all we have in the online chat or Q&A function. We're obviously a little early in terms of our allocated time, but we'll just reiterate, if you have any follow-up questions that didn't come up today, please feel free to reach out directly to either Jesse or myself, and we'll do our best to answer them. And just got one more slide here. We wanted to thank you all again for joining us. We really appreciate it. On behalf of BAR, we hope you got some value out of this presentation today, and thanks again. Hope you have a safe rest of the day, and we look forward to welcoming you to our next webinar. Until then, take care and goodbye.